Hey everyone, myself Bhavya Goyal, a student at IIT Gandhinagar. I welcome you at CodeChef and let's have a look at this question. So yeah, today's question is ones and zeros too. In this question, we're given a binary string f of s, which is defined as follows. So a prefix s from 1 comma I is called good if it contains at least s with 1 and zeros. So if the count of ones is greater than or equal to the count of zeros, in that substring or in that prefix, then we call the prefix to be good. Now, f of s is the number of good prefixes in the whole string s. So this is how f of s is defined on a string s. Now we are given a binary string s, which is of length equal to n, and our task is to maximize this value f of s by performing adjacent swaps only. So if there is 1 0 1 1 0 1, we can perform this swap, which would be considered as one operation. And we need to figure out that what is the maximum possible value of f of s that we can obtain by doing the minimum number of swaps needed to obtain that maximum value of f of s. Now, obviously, an adjacent swap is defined as choosing an index I and swapping s of I and s of I plus 1, where I is in between 1 and n. So that's pretty much the whole question. It will be a bit more clear once we see the sample inputs, but for now, let's see the constraints. So the constraints are given that the number of test cases would be in between 1 and 10 is to the 4, and will be in between 2 and 2 into 10 is to the 5. The length of string s would be n, and each element of s would be 0 or 1. That means the string s is binary. And the sum of n over all the test cases would not exceed 2 into 10 is to the 5. So basically, we need to come up with some of n or maybe some n log n or something of similar order solution which can pass in these constraints, right? So now let's once see the sample inputs. So in the first input, we're given all three zeros. So there is no possible prefix where we can have more ones than zeros because there is no one, right? So the answer is zero for both of them. In the second, we are given 0, 0, 1. So we can do two swaps and obtain 1, 0, 0. In this string, we have this prefix where the number of ones is greater than or equal to the number of zeros. And this prefix also where the number of ones is greater than or equal to the number of zeros. So they are in total two number of positions where the number of ones is greater than or equal to the number of zeros. Hence, the maximum f of s that we can obtain is going to be equal to 2. And we require two operations to do that. Hence, the answer is 2, 2. In the next, we are given 0, 1, 1, 1, 0. Now, the most optimal string that we can obtain here would be 1, 1, 1, 0, 0, or maybe 1, 0, 1, 1, 0. Yeah, this is the most optimal string that we can obtain from this. Now, how many operations did we do? So we just swap them. So the number of operation that we did was equivalent to 1, right? And if we count the number of good prefixes, this is a good prefix. This is also a good prefix because there's 1, 1 and 1, 0. This is also a good prefix because there are two ones and one zeros. This is also a good prefix because there are three ones and one zero. And this is also a good prefix because there are three ones and two zeros. And all the five indices are good, and we cannot get any better than five, right? Because there are in total five indices only. So the maximum possible answer that we can get for f of s is equal to 5. And the minimum operations that we need to do is 1, right? Because in zero operations, this does not give us 5 good prefixes. And we can just see the last input. All of them are 1, so we just obviously don't need to do any operation. And the maximum number of prefixes and dices we can get is 5. So that was all for the test cases. Now let's see the solution ones. So yeah, let us first of all try to think about what is the maximum possible f of s that we can obtain. So if we have, let's say, some s like this. So without worrying about the number of operations we are trying to minimize, what is the maximum possible value of f of s that could be good, that we can get? So one way or one arrangement is to put all of these ones in the beginning and then just put all of these zeros. So what is it gonna do? it's gonna increase the count of ones, and then there would be some zeros which you can accommodate. So for here, for instance, over here, this is good, this is also good, this is also good, this is also good, this is also good, and this is also good. And beyond this, it would never be possible to get a better strength because a better like answer because the number of ones would never be more than that, right? We cannot have more ones than that. So the maximum possible value of f of x would be the minimum of 2 times ones, like the count of ones, and each one can carry one zero as well, right? So this one will counter this one zero, this one will counter this zero, and this one will counter this zero. And we cannot get any bigger length than this. So the maximum f of s would be min of 2 times 1, comma n. So let's say if there were like more ones, if all of them were ones, then 2 times ones would be 12, right? But the length of string is only 8. So the maximum possible answer would be 8 only, right? So f of s would always be min of 2 times 1 comma n, right? Now let's try to minimize the operations. So first of all, is this arrangement going to give us minimum operations? Will it? So the answer is no, obviously, right? Why? Because in this construction, how many operations do we need? One operation to solve these two, and then one, two, three, four, five. Five operation to bring this one till here, right? So in total, we need a number of six operations. But we can do much better by just bringing this one over here and keeping rest everything the same. And we'll just need three operations with the most optimal solution for this, right? So how can we find the minimum number of operations for a for the most optimal solution? So let's just see a few small cases to understand the problem better. So let's say we have zero one, something like this, right? So do we have to swap, like do we have to bring this one in the beginning? Obviously we have to in an optimal solution, right? So one zero would be the most optimal solution where we'll have the answer as two and the minimum operation as well. In this zero zero one, again the most optimal way is to make it 100. Right. Now again, over here, the maximum f of s is 2, and the minimum operations we need is also 2, because we need to bring this here. Would 0, 1, 0 be a better solution? No, right? Because f of s would be 1 only here. And in this also, let's try to see what would be the most optimal way. So it turns out that the most optimal way would be to bring this one over here, right? So we can do 1, 0, 1, 0, 1, and we can get the f of s is 5, and the minimum operations is 2, right? Now, can you observe one pattern? In all of these optimal solutions, each of the prefix is always going to be good. So this prefix is good, this prefix is also good. This is good, and this is also good. Oh, sorry, this is not good. So up till some index, all the prefixes would be good, and then none of the prefix would be good in any optimal solution, right? Like over here also, this is good, this is also good, this is also good, this is also good, this is also good. But if we had, let's say, two or three more zeros, then this would have also been good. But from this point, it would stop becoming a good prefix, right? Now, will this be the case every time, right? Like this is our observation right now, that each prefix must be good till some point in an optimal solution. But is our observation correct, or is it like just a mere observation which is working in these three cases? So let's try to prove this observation. So basically, we are saying that some string like this can also be optimal, where not each of these is a good prefix, right? So there can exist some string like this. But in any such string, we can always find the point where the prefix is not good. So this was a good prefix. Okay, this was also a good prefix. This is not a good prefix. And then this turns out to be a good prefix, right? So can't we just swap these two elements, make it 1, 0, and this would just increase our count by one of, and it would never reduce our count, right? Because now this is a good one, this is also a good one, this is also a good one, and this is also a good one. And further, we have not, like, it doesn't matter, right? So even up till this index, we have found a better answer without impacting on the future values, right? Because for the future, the number of ones would remain to be the same, and the number of zeros would also remain to be the same. So it turns out that, okay, our observation is correct. Each prefix must be good until some point, right? Because if it is not, we can always do such swap and make it better. right? Now, how would we solve this? Right? How would we figure out the minimum number of operations? So for that, let's think about a greedy algorithm. So we'll keep running. So right now, we need that up till this index, everything must be like good, right? Every prefix must be good. So let's call this index as R. Right. This stores that up till which index, which is the last index where we want this string to be good. So, okay, up till there it is good. Right. Now we'll iterate over the string. Okay, up till this, okay, this is a good string. We are good to go. Now we are on this index. Up till here also the string is good, right? So it's pretty good to go. Now, now because up till here we have found 1, 1, we can say that this much part of ours is sorted, right? This much part would be good. Right. So we can bring this R till here. That okay, from this index we need to figure out if it is good or not. Right. Like we need to bring someone over here so that it still remains to be good if there is no one. Right. Like at least we need at least two ones up till this index to make it like keep it good. I will just keep it reaching. We have this index. Our string is good. Okay, so we are good to go. We have found another one. So we have found two ones. So two ones means up till index 4, we are good to go. Right. Up till this index, we don't need any, like we don't care much. We will keep iterating. Up till here also the string is good. We are good to go. Up till here, the string is not good, but do we have any buffer ones? We don't have, right? We will go over here. Can we do anything better? No. We'll go over here. Can we do anything better? No. We found a one over here. So it's better to move this one to this index, right? So that all these prefixes remains to be good, right? Like this R was the first index where the string stopped becoming good. And now because I is greater than or equal to R, we can swap them and add an answer of I minus R. Right? We'll just add this thing. This 1 will come here. This 0 will come here. And this R will come over here. Right? Because up till this index now, the string is good. All the prefixes are good. Now we'll increase the I. Okay. Yeah, this becomes a 0. This is a 1 now. This is a 0 now. Now our I is this. And now finally our I is equal to this. Now again we found a 1. So it's better to replace this 1 with that R index. So we'll replace this with this one and replace this with this 0 and we'll move this R towards this position, right? And this is pretty much how the algorithm will work. And this will give us the minimum number of swaps we need, right? Because we are only swapping wherever it is absolutely necessary. And that's pretty much the whole solution. We'll discuss it once more in the code just to make it crystal clear. And now let's just move to the code only. So yeah, this is the solution in C++. So we begin by taking in the input of n. We take in the input of string s. We count that how many ones are there in our whole string. And this would be our f of s, that is min of 2 times 1 comma n. Now, this is how we'll calculate everything. So if our s of I is equal to 1, and if our I is greater than or equal to r, that means r is the location where 1 needs to be present, so that the property of all the prefixes being good does not break. So we need to bring this 1 to that index r. So we'll bring that till that index, right? And at every occurrence of 1 will increase the count of r by 2. Because everyone is saying that, okay, I can accommodate these two people and just increase the count by 2. And that's pretty much the whole solution in C++. The time complexity is big of n. Now let's see the solution in Python. So we'll begin by taking an input of n and s. This ones will store the count of ones. And this max count is nothing but our f of s, which is 2 times 1 comma n, min of 2 times 1 comma n. And we'll print this max count. Now let's count the minimum number of operations to get that f of s. So this r stores the index where a 1 needs to be inserted so that the property that every prefix is good does not break. Right? Now we'll initialize our answer by 0. We'll run a loop from 0 to n. If s of I is 1, then first of all the r will increase by 2 because we have found a 1 which can be placed at that index. And now that 1 can accommodate for two places, right? For itself and another 0. So we'll increase the r by 2. Now if I is greater than or equal to r, we'll increase the answer by I minus r. That this 1 needs to be brought at that place at that r, right? And that's pretty much the whole solution. The time complexity is big of and yeah, that's pretty much the whole solution. I hope you like it. Thanks.